Everyone, this is Oscar, and today we're going to be working a problem from Calculus 3. This problem states to find the directional derivative of the function at a certain point in the direction of a vector. So we're given our original function, we're given a point and a vector. So the easiest way to find the directional derivative is taking partial derivatives of our function with respect to x, and then it'd be partial derivative of our function with respect to y. So you have uh, this, this would be like part of a function, and then you want to take the dot product with our unit tangent vector, okay? And then after solving this, you'd want to plug in the given point, which is 0, comma, -4, and it should give you the directional derivative. We also want to review how to find the unit tangent vector, but we'll do that after finding the partial derivative with respect to x and y. So in our original equation, f of xy is equal to x times y. And that's written here is our original function. And if we take the partial derivative with respect to x, then we're just given y because the derivative of x is just 1. And then if we do partial of our function with respect to y, then we're just given x. So this can be written as y, x, and then we just want to find the unit tangent vector of our original vector. So our original vector, I'm just going to change colors here. Our original vector is written as 1/2, and then our y value is square root of 3 over 2. Now, to find the unit tangent vector, which is written up here, it's going to be our vector over our vector magnitude. So, if you guys know how to find this vector magnitude, this is each component, it has to be squared and then added to the next component squared and then under a square root. So this would be 1/2 squared plus square root of 3 over 2 squared, and then this whole thing is under a square root. So we'll do that math. It's basically testing a little bit of your algebra skills. We'll make some room here. This would be equal to, so 1/2 squared is just 1 over 4 plus, so if we have, you could think about it like this, square root of 3 squared would just be 3 over, so if it's 1/2 squared, it'd be 1 over 4, so this on the bottom would just be 4. So this is addition. If you guys should be able to add this up, it'd be 4 over 4. But remember, this is all under a square root. So it'd be a square root of 4 over 4, which is the square root of 1. And the square root of 1 is just 1. Okay, so if we go back to our form of finding the unit tangent vector, it's our vector divided by our vector magnitude, and we found that vector magnitude to be 1. So basically, our original vector, which was 1/2 square root of 3 over 2, we would have to divide this by 1, but then it's just itself. So our unit tangent vector is actually just a vector itself. But if you guys have a different problem, the vector magnitude might not always be 1. So if you find out that the vector magnitude is something different than 1, then you'd want to do this math, and that would be your new unit tangent vector. So this could be any number, and you just have to divide through for each component. So if we go back to our equation here to find the directional derivative Our unit tangent vector over here is just 1. So just let me clear up some space. And these two right here are actually dot product. So wait, this is not actually just 1. It's our original vector. So this is dot product. So it'd be written as y x dot product with 1/2 square root of 3 over 2. And then dot product means you multiply each corresponding component and then you add. So this would actually just be 1/2 y plus square root of 3 over 2 x. And then this is where you would plug in the point. And it says our point is at 0, -4. So this would be our x value and y value. So our y value is -4, so this would be 1/2 times -4 plus, so square root of 3 over 2 times x, and our x value is 0, so it'd be 0. So this would be simplifying -4 over 2, and -4 over 2 is just -2. And that would be our final answer. That would be the directional derivative of the function at a point in the direction of a vector. Thank you guys. I hope this helped you. And good luck solving any more problems.